Today, we are here to talk about why standards matter. And in addition to that, the ones that you'll want to know about in the wireless profession. Now, the reality is that there are hundreds of standards that you might interact with, touch, come across, have to troubleshoot, analyze, etc. in your work with wireless networks, because there are many different types of wireless networks, first of all, right? We have, of course, 802.11 Wi-Fi, but we also have 802.15.4 based wireless networks. We have industrial wireless networks using things like ISA 111A, Wireless Heart, and others. We have Bluetooth networks and Zigbee networks and cellular networks, LoRaWAN, Sigfox, and the list goes on and on. So there are all kinds of wireless networks. And then when you look at the upper layers of communication, and we'll talk more about layers in a few minutes, you've got a ton of possible protocols that are being used there and therefore standards. And so literally it is in the hundreds, although it is actually simpler today because most of the communications that we use are standards based now, and that hasn't always been the case. And that does help us. So standards are good, and they help us to have a consistent way of communicating. And so that is just phenomenal. So we're going to talk a bit about standards first, then we'll look at some of the standards bodies, the organizations that create standards, and we'll wrap up by looking at standards and asking the question, how do we read these things? How do we find what we're looking for in these things in order for them to be helpful to us in troubleshooting processes, design processes, and other such things as this? So we will begin, first of all, by exploring the reality of these standards, what they mean to us, and how we work with them. So first of all, the standard definition. And the reason I say this is, interestingly, and I have a image of it here. There was a editorial written back in, I believe it was 1981, if I remember right, that I pulled this screen grab from, titled, "What is a Standard Anyhow?" And the individual writing this gave a number of definitions of a standard. And then, of course, the last one was his preferred definition: a formal, consensus-developed, publicly owned, concrete specification amenable to conformance testing and broadly available. So that was his desired definition, but there were some really intriguing ones in here. I loved number 10 that you can see in this image: an opportunity offered by big vendors to the little vendors to show the big vendors where markets might exist without risk to the big vendors. And this has really been true in the history of standards development. Big vendors quite often said, well, hey, here's how your technology, little vendor, can integrate with our big vendor network. And then what happens is the big vendor says, oh, okay, I see that this little vendor is participating a lot in the automobile manufacturing space, or maybe in the shipping space, or whatever industry it is. And they say, what we need to do then is create marketing literature that markets our big vendor solution that will supplant the little vendor solution into those same verticals. And there was a lot of that happened. And then, of course, the big vendors have always played a role in standards because they have the experts on staff to participate in the standards development processes, and they have the dollars to spend for their employees to travel to wherever the meetings were in the early days. Nowadays, a lot of these meetings are online, or they're mixed between online and in person, all at the same time. So there'll be video streams for those that can't attend locally. So over the years, the standards development process has moved more and more toward being open for little vendors to play their part, and even people that aren't with vendors to play their part. We see more of that in the IETF than we do in the IEEE. But the reality is that vendors play a big role in developing standards, and a lot of them have enough influence to send enough delegates to the standards development processes so that they can sway a lot of people to their way of thinking. And that's the goal that they have in that process a lot of the time. And it's not necessarily that it's malicious intent. It's simply selfish intent. We've got this technology already. If we can convince the standards body to make it the standard way to do things, then we don't have the development time involved that others might to get up to speed with the way of doing things, right? And so you see that in standards development processes. But here's a definition that I'll give you that I think we can go with. We can say that a standard is an established norm or requirement, typically a formal document or set of documents that sets out specific criteria, methods, rules, and conditions or practices. And so, in other words, it first of all is established. Now, is this established just over time as the way people eventually evolved to doing things? Or is it established by a group coming together, forming consensus, and then documenting it? Well, both of those can be a standard. We have what we call de jure standards and de facto standards. De jure standards are formal standards, right? So these are documented. These are the steps that we go through in this standard process. And by the way, standards are not limited to computer communications, computer data formats, things like that. Though we have those, so we've got protocols that are standardized. We've got data formats like JSON and XML and different flavors of XML that are standardized. So we definitely have them in the technology space. But the reality is that standards exist all over. There are standards for the spacing of threads on bolts. There are standards for fire retardant materials and on and on. So there are standards all throughout the manufacturing, engineering, and product development and supply space. But the difference between the de facto and the de jure standard is simply one of them is a formalized standard and the other is based on common use. And sometimes it can be a de jure proprietary standard that becomes a de facto standard. Now, by that I mean that technically a proprietary standard would be a closed standard, one that one organization or some collective group defines and they don't allow others in, right? So it's proprietary to them. They build the standard. But just because it's proprietary doesn't mean that they don't make it available for people to implement. And so it can be proprietary and available to implement, or it can be a completely open standard. And this means that it is a standard that is developed and may evolve over time through consensus, different people coming together to decide how the standard should be changed or should evolve. An example of that would be the 802.11 standard. It would be the IETF standards that are developed for internet communications and so forth. These are open standards that are in the de jure or the formal category, right? And then, of course, de facto standards, as I said, are just the ones that people commonly begin to use. We see this with data formats. It's not uncommon for an individual organization to create a data file format that they then may make the specification for that data file format available. And then other people start to create applications that can open that file, manipulate that file, present that file, and so forth. And that file may become a sort of de facto standard over time. Though it's not really created by a standards body per se, it's created by a single company that developed that data format. And yet it's widely used by a lot of different applications eventually. And sometimes what you find is that company that created the file format actually ends up with a very minor share of the market for the use of that data format as it becomes that de facto standard. And then often what happens is the de facto standard gets pulled into a formalization group and they make it a de jure standard. In other words, they create an open standard for that particular format, protocol, what have you. So these are the standards, right, that come along. Now I'm going to use an example of a standard, and we'll see how these things may evolve over time. And the example that I want to use is the OSI reference model, we call it today. The OSI reference model, created by the ISO, the International Organization of standards, or of standardization, and they created this starting in the 1970s and finalized the early versions of it in the 1980s. Now, the reason I'm using this as an example is we see that it definitely evolved over time. This image that I present here is from a journal/magazine. It was kind of one of those that crossed over. It was almost like a journal and a magazine all in one, but it was called Computer Communications. It is still called Computer Communications, and it is more of a journal today than it was back then per se. And there was a paper in there called OSI Protocol Choices for LAN Environments, published in 1990, January, February of 1990, so very early in 1990. So that's 35 plus years ago now. And this is showing the OSI model, application presentation session, transport network. Then they say logical link control and medium access. So a little different terminology being used in this diagram than even what the OSI spec had at that time, interestingly enough. And the key thing I want to point out is the things that are in here that, particularly if you're really young, you've never even heard of. But even if you're older, you may have never heard of them, because most of them didn't actually make it into any type of large-scale, multi-company, multi-network implementation and use. So we see things that you may have heard of if you're a little bit older, like me, like X25, but you heard of it as X25, not as ISO 8881.3. Okay, so basically ISO 8881.3 was the ISO specification for use of X.25 as the network layer for an OSI implementation. And then ISO 8473 was the specification for the use of the Internet Protocol, or IP, as the network layer of an OSI implementation. Okay, so the way this happened was throughout the 1980s, when you looked at either the journal articles written about the OSI model or magazine articles and even books that referenced it, though we didn't see a lot of books referencing it until 84, 85 timeframe. But these different reference materials would refer to the OSI protocol rather than the OSI reference model as we think of it. So the thinking of the people in the network engineering realm was that the OSI model was going to actually be implemented as a set of protocols. And indeed it was, but there wasn't really an OSI protocol for the physical layer. There wasn't really an OSI protocol for the network layer and so forth. Instead, you would use a protocol as the protocol for an OSI implementation. This is the way it evolved throughout the 1980s. So what started in the thinking of a lot of people as the ISO is going to give us protocols became, we've got this way of thinking about networking. So by the mid-1990s, you never really heard anyone refer to an OSI protocol anymore. By that point in time, IP was clearly winning. The internet was taking off 1993, 94, 95, 96 throughout that time. And really by 97 and 98 had exploded in growth. And then by the year 2000, there was no question which protocol suite had won the day. And that was TCP/IP. Throughout the early 90s, there were battles between IPX, SPX, Banyan Vines, TCP/IP, and a few others used on local area networks. But by the end of the 90s and in 2000 and beyond, it was clear that IP was the winner. And it still is today. Now, of course, it was in the late 1990s that we had the concerns over the IP version 4 address pool and the fact that we just don't have enough IP addresses. Well, interestingly, worldwide, just looked at some research that came out earlier this year. Worldwide, IPv4 is still the majority use between IPv4 and IPv6, meaning that more than 50% of all of your IP communications that are happening are IPv4 and not IPv6. In some countries, it is as high as 70% IPv6. But worldwide, overall, in the aggregate, we're still looking at the fact that IPv4 is the dominant protocol. And I remember in the late 90s, it was not quite at the level of warning and fear mongering that we had over Y2K. And if you don't know what that is, go do some research on the Y2K bug. But it wasn't quite at the same level as that, the Millennium bug or the Y2K bug. But there were people already starting to sound off and say, oh, we've got to replace IPv4 with IPv6 within the next 5 or 10 years. And somewhere in that range, people would usually say. And here we are now 25 years later, and we found ways to keep on using IP version 4, which of course is an IETF standard. Okay. So I bring this up to kind of illustrate that sometimes a standard doesn't evolve in the way we expect it to. Sometimes it goes in different directions. And so sometimes early on, there might be things in a standard kind of thinking that people may use this, people may implement this. The only pain point is that if it's in the standard and just a very few people implement something, or there remains the slightest hint that someone might tomorrow implement it, it can remain in that specification for a very long period of time. We've seen that in the 802.11 standard, for example. So what the OSI model eventually became was a reference model. That's the way we think of it today, right? We think of it as a way to talk about and think about networking. There are a lot of people that make arguments, so we should quit even talking about the OSI model. We should instead refer everything to the TCP/IP model. Well, I do understand that, but there are still communications out there that are not TCP/IP, and we can fit TCP/IP into OSI. And so, we can talk about it in that way. Relatively, sort of, kind of. And so I think that, hey, as a common language for network communications, it still works. And so we've got these terms that we use in networking communications. And here's one of the big reasons we have to keep holding on to OSI, because many other networking standards refer to this terminology. And so they may say, it's an application layer protocol or a layer 7 protocol, or it's a transport layer protocol or a layer 4 protocol or something like that. And because they may use that kind of terminology, going through all the standards and weeding out this language of networking that evolved is very challenging to do. And that's the best way to think of the OSI reference model now, is defining a language of networking, a way that we talk about networking. So instead of saying, communicating across the wire, we talk about physical layer communications. Instead of saying communicating across the RF medium, we say physical layer communications, right? So it's just a language that we use today. Now, how standards actually get implemented over time in the real world, well, there's something that is often referred to as the technology adoption curve. It's also sometimes paired, as we see in the image here, with the Gartner hype cycle. So the hype cycle is all about how people go through a phase of everybody's talking about it. Nobody's using it, but everybody's talking about it. Now, when I say nobody's using it, a very small percentage, usually somewhere down around 7 to 15% of the people that could use it are using it. And we are in that innovators, early adopters era. That's the early stage of the hype cycle. And then what tends to happen is you go through disillusionment. That's the red line here, the Gartner hype cycle, which creates Jeffrey Moore's chasm. You may have heard of the phrase crossing the chasm. So Jeffrey Moore came up with this concept of this phase where if we don't get across the chasm, then we don't get to the point of something becoming a mainstream technology, right? That's really the simple way to think about it. And he came up with this concept of the bowling alley and the tornado. So the bowling alley is, think of it as in the early stage of moving from early adopters to the early majority, where in niche markets, the technology, whatever it is going in and taking over it. Each of those niche markets is a bowling pin, right? So we're knocking down each of those markets. And so we're doing it piecemeal by piecemeal, but eventually it gets to the point where there's momentum and it's like a tornado and it carries it ahead. So that's just the metaphor that is used in that model. The key thing is that not everything makes it across the chasm. Whether we want to think of it as a chasm or something else, not everything makes it across. And some things die before they get to that level. There are many standards that have been released over the years that we may not say they never went anywhere, but they're now a forgotten thing of the past. They were not the winner in the end because when they came to the chasm, they didn't make it across and someone else did. And by the way, here's another way. I love this from businessillustrator.com. This way of representing it I thought was cute and definitely a good way to think about it as well. I like the little shark fin in the chasm that is the dreaded waters of getting through to becoming a mainstream technology. So any standard has a chance. This is the point. Any standard has a chance, but not every standard is going to become the winning standard and get into that category of the norm, the thing that everybody uses, like IP did, right? So IP was able to cross the chasm between the late 80s and early 90s, and there was something that made that happen. And what the something was, in this case, was the internet. IP didn't invent the internet. IP was invented for what eventually became the internet, right? So the folks at DARPA put together this protocol for their network. And then when colleges started wanting to plug in and all these different companies eventually wanted to get on the internet and all of it started happening, well, the protocol used was IP, right? So, hey, if we're using it on the internet, why are we using IPX, SPX, and TCP/IP both at the same time on all of our client computers just in order to have them be able to talk to our local servers across Novell NetWare and also go out to the internet and browse web pages? Maybe we should just switch over to IP internally. And it just made logical sense to do that, right? And so that was kind of the flow of what happened. It was what helped IP across the chasm and become the standard. It wasn't necessarily that IP was better. It was the way to connect to this thing called the internet if you wanted to participate on it. I'm not going to get into the arguments over whether IPX, SPX, or TCP/IP was better or something else, whatever the other protocols might have been that were competing. But there were plenty of those going through the mostly early 90s before even those that might have said they had good arguments for other protocols, they knew they lost the battle. And so it was time to switch over. And so, yes, we crossed the chasm, and hence my wearing of the mountain shirt today, because with any new technology, we have to climb up a mountain as we're making it the standard. And part of a standard winning is the technology community supporting the standard today, because there's a lot of influence that comes from the technology professionals. So educating yourself on what standards are out there, what hardware and software exists supporting those standards, and which ones best meet the solutions in your organization become an important thing that do end up influencing the technologies that win. And this is why we see, for example, in certain areas of industry, one protocol is the most popular way to do things. And in another area of industry, another protocol is the most popular way to do things, because the OT people in this area, they went with wireless HART. The OT people in this area, they went with ISA 111A, if we're talking about wireless industrial protocols, right? And so you see people choosing what their niche of the industry tends to go with. And you see that an awful lot even still today. So it's not just which standard is necessarily best. There's a lot of influence that comes from the culture and sociological drivers that impact a lot of this as well. That's just reality when we see technologies that win and technologies that lose. All right, so let's talk then about the organizations that help make all of this happen. And the first big player that I'll address is, of course, the IEEE. So the IEEE, what we're talking about here is the Institute of Electrical and Electronics Engineers. Before that, it was just IEEE and some connections with IET. And anyway, they've been around a long time, a very, very long time. So the transactions of the IEEE eventually becoming the transactions of the IEEE. They have been published for 100 plus years. And when I say published, I mean it's a journal. The transactions is a journal. And so they've been involved in standards development for all that period of time. Obviously, they weren't always developing computer networking standards, right? Because there weren't computer networks. Instead, electrical engineering, right? Institute of Electrical and Electronics Engineering, or engineers. And so they were involved in a lot of things before computer networking came along. But for our discussion here, our main interest is what they're doing related to networking. And the biggest area of that is in the 802 standards. So we have 802.2, which defines the logical link control specification, or LLC. This is the standard for the upper portion of the data link layer, the LLC sublayer of the data link layer of the OSI model. And then they define MAC specifications for MAC and PHY, the 802.3 Ethernet, 802.4 we don't really deal with anymore, 802.11 for Wi-Fi, for example, 802.15.4 for low power IoT, WANs and LANs, mostly LANs. The range is not sufficient for wide area networks. But there are some long distance communication capabilities depending on how and which PHY of 802.15.4 is implemented. And long distance, it's everybody's opinion as to what that is. You know, some people might say, well, 2 kilometers is a long distance. So these are different standards that the IEEE provides. Now, one of the key things, if you go into your 802 or your IEEE standards, is that you can search for your different standards, and you can see they'll spotlight any kind of developments that might be going on within the standards development. So if you do a search for the standards, the best thing to do is to come up here to the IEEE Explore digital library, and then you can choose standards. And if I search for 802.11, I will see that we have here, for example, the 802.11 2020 Core Addendum 1 from 2022. We have the 802.11 2012. And going on down, you'll see the 802.11 2016, 802.11 2020, 802.11 2012 Red Line Edition. And oh, look at that, 802.11 2024, which finally published in the last few weeks. It was ratified as the final draft, and I'm going to say August, but at the latest it was September of last year, but I believe it was August of last year. And they just finally published, so you could access it, the final version of 802.11 2024 a couple of weeks ago. So that is the latest roll-up of the standard, right? So when I say the standard, what are we talking about? Well, we're talking about a document like this. So this happens to be 802.11 2020. I haven't downloaded 2024 yet. I'll be doing that this next week. So you can see this one was already 4,379 pages long. Some of that is front matter, some of that is appendices, but appendices are important in the standard. And the standard for IEEE is broken down into clauses. Clauses are just chapters, if you will, sections that focus on specific things, right? So we have, for example, definitions and acronyms, a general description. How does the MAC service work? How does the PHY service work? What are the frame formats? So all of this is defined within different sections, and then you'll have physical layers within the specification. So we've got different physical layers that allow for different types of radio communications, different kinds of modulation, different channel bandwidth specifications, and so forth. So all of these things are what these different physical layers specify, how the physical layer is utilized for communications. And of course, generally speaking, later PHYs, at least within the 2.4, 5, and 6 gigahertz bands, give you higher data rates than earlier PHYs. Now, we can't just say that later PHYs always give you higher data rates. That's why I qualified 2.4, 5, and 6 gigahertz, because S1G is a later PHY than some other specifications, and yet it's not a faster data rate than 802.11n necessarily could maximally achieve, because it's for a different purpose. It's sub 1 gigahertz, right? And so we have all of the physical layers specified that we can go into and find out how they work. Now, how do you use the standard? Well, let me back up for just one moment. First of all, let me say, where do you get it? So there's a program the IEEE offers called Get 802. So if you just go to your favorite search engine, do a search, all one word, Get 802, Get 802, the digits 802. And you'll find where you can download the 802.3, 802.11, etc. specifications. And generally speaking, about 6 months after publication, so 6 months from now, roughly, you can download any of the standards that are published, but you have to pay for them early on. Okay. So right now you have to pay for 802.11 2024. Generally speaking, in about 6 months, you'll be able to download it for free. Right now, you can download 802 2020. You can download amendments like the 802.11ax amendment, things like that, and so forth. So you can download these files through the Get 802 program. You can get Ethernet there, and on and on. The benefit of having the standard and using the standard is that when you want to know how something works, this is the baseline. This is the spec. This says how things are supposed to work. And it can be very useful in the troubleshooting process to understand that. And yes, we can learn how it works from books and videos and things like that. But when you want to verify, particularly if you watch one video on YouTube and it says, here's how this works, and then you watch another one and it says, here's how this works. Well, then the reality is that if they conflict, you need to find a resolution, right? And so to find that, go to the standard. Now, just because the standard says it works a certain way does not mean that your device is doing it right. So sometimes, for example, you can use protocol analysis and you can see how things are implemented and see, oh, there's a bug in the driver for this device or for this piece of hardware because it's not forming the frame headers appropriately. And then you can communicate with the vendor, whatever, you can try to resolve the issue. But you can only do that if you can go back to the standard to see how it works. Don't let the standard scare you. If you're, especially nowadays, we've got solutions to help us. You know, if there's a section you're looking at, and you're not fully understanding what it's saying in a couple paragraphs, copy and paste them into your favorite large language model and say, hey, can you explain this to me? Now, it may not explain it 100% accurately every single time, but generally speaking, I've found that when you do that, they give you a pretty good idea of how it works. If you just go in and say, explain to me how CSMA-CA works in 802.11, then yeah, it might get some things wrong. But if you actually paste the technical jargon of the standard in there and say, explain this to me, then they tend to do a lot better. Okay. Now, the next organization that I want to talk about is the IETF. So the Internet Engineering Task Force, they've been around for a long time, and some of the standards that they've developed began to be developed actually in the 1970s. And they became documents that were released as part of the collection of standards when the IETF was formed. The IETF defines standards for internetworking protocols. And so they are giving us the specifications for how the internet works. Okay. It's a simple way to think about it. And when you come here, of course, you'll see that you have the ability to search for standards, and you can then find the standards you're looking for. Now, what I have found is it's generally easiest to just go to your favorite search engine and search for RFC and then the thing you're looking for. So if you're looking for IP version 6, search for RFC space IPv6, because the IETF uses requests for comments, RFCs, as the way to publish standards, okay? Basically, someone publishes a draft, they're requesting comments on their draft, right? And then, and that someone might be some group, but they publish the draft, people make comments, they incorporate changes, people make more comments, they incorporate changes, and then eventually they have a vote and they finalize it as the ratified version of the draft. And then later on, they may end up amending it, changing it, and that obsoletes an earlier version. So for example, if we look at our RFC for the Extensible Authentication Protocol, that's what we have here. This is RFC 3748. Notice it obsoletes RFC 2284. And so this is basically the replacement for RFC 2284. Now, here's where things can get interesting, right? With IETF standards, if you're going to look for them, you do need to know what you're using. So if you're using in your communication system 2284 and not 3748, then you want to look at 2284 to see how your system works. So you might have an old system that uses an old technology. That's unlikely with EAP because, 3748 has been the current version since 2004. So it's unlikely that something would be using something older than 21 years ago, but it can happen, all right? It can happen. So you always want to know what you're using and then look for the RFC version that matches what you're actually using. This is why, for example, with a standard like SNMP, you might be using a version of SNMP that's not the latest in some older system, and you want to look and see what it does, what it doesn't do, what features it has. So you might be reading in a book about a protocol, and the book says the protocol can do X. You look throughout your system, you can't find anywhere where you can configure X. And the reason may be that you're using an older version of the standard in your system. And therefore, you're unable to actually do X because that was a feature of a later version of the standard. So find out what version you're using and you can go from there. And sometimes you can go to the vendor documentation and figure that out. If you're dealing with a situation where the vendor's out of business and you can't get documentation for your technology anymore, then one of the things you can actually do is capture the communications from the device. If you have the ability to do that, capture the communications, look in the communications, and there might be a version field for the protocol, whatever it is, and that can tell you then the version that you're utilizing. So look at the older versions of the spec, look at the format, the structure for the protocol. So one of the things they'll do is they'll have structure for packets or frames defined. So if we scroll down here in this one, let me just zoom out a bit so I can scroll faster. All right, so we see some communication structures here. And eventually you'll probably see, here we go. So here's a type field, a length field, an authentication protocol field, right? So this is what I mean when you look at the structure of the protocol, this is what you're looking for. And this may have some type of a version field or some other field type that's going to tell you what version of the protocol you're actually utilizing, okay? And that's the kind of thing you can look for to find out where you need to go from a standards perspective to see how your system is actually working. Now, myself, as much as I love 802.11 and I love wireless communications, and the vast majority of those standards are in formats similar to IEEE formats, whether that's through someone like the Bluetooth SIG or whomever. The reality is that of the standards I enjoy reading the most, I like the IETF standards. I just find that they're more naturally written standards. They're easier to understand, but there's no precision that's sacrificed. So I don't know why we always have to why standards have to be written in a language that makes them more confusing than they need to be. We definitely need accuracy and precision, but sometimes I think that the IEEE standards can tend to be written in ways that are maybe stuffier than they need to be in order to get the communication across in a precise way. But that comes to the background, historical source of the organizations, things like that do influence the style and so forth of these types of standards. So you can figure them out, though, with a bit of effort and time. So that's the RFCs. And again, you can find them for internet type standards like IP, TCP, UDP, SMTP, these types of things. You will find standards in RFCs. And then you may have RFCs for different EAP methods as well. And then there are EAP methods. Since we're looking at EAP, I'm specifying this. There are EAP methods that were proprietary, right? They were developed by a specific vendor, and they provided the supplicant, the client software for those EAP methods, and you had to use that in order to work with that vendor's EAP method and so forth. And so just because some part of a system is a standard doesn't mean every part of the system is a standard, and the system might break if you don't have the ability to use that proprietary piece of the puzzle. All of this comes into play when we're choosing and building the solutions and systems that we deploy in wireless and otherwise. Now, let's finalize our discussion of standards by going over a few other groups that are out there that are important to know about. So the Wi-Fi Alliance is obviously very important in the Wi-Fi space. They not only certify hardware to be compatible with or compliant with some subset of the IEEE specification for 802.11, but they do also define their own specifications as well. So some of the things are defined by aggregating together technologies that other people have specified in things like hotspot 2.0, things like that. We see that there's an amalgamation of other people's standards, and they're simply saying this is how it will all work together. And then there are also specifications for the most part are built up from them. But they publish their specs out here. If you go under certification, you can find the different certification programs that are available. And then you can read about those programs and see what they cover. And you can see there are a myriad of them. All right. Then you have the ISO. They developed the OSI standard, right? But that's not all. So there are things where you'll see an ISO/IEEE standard, or an ISO/IEC standard, or an ISO/IEC/IEEE standard, or an IEC/IEEE standard. In other words, you will see that the ISO and the IEC, which are international standards organizations, will tend to integrate with the IEEE, which is also an international standards organization, right? So they'll sometimes work together and create standards. For example, when we test on requirements engineering, as far as understanding the general process of doing that, we do it based on standards. And the standards, which we generally just call, to keep it simple, IEEE 29148-2018, well, that's actually an ISO, IEC, IEEE standard, right? So it's a conglomerate standard among the organizations. And then you also have similar things with 15288 for the lifecycle processes of systems management and things of that sort. So you'll see a lot of integration among those. Then you have the Connectivity Standards Alliance, which is the new version of the Zigbee Alliance, right? So they wanted to go beyond just being known about Zigbee. And so they have become the Connectivity Standards Alliance. And therefore, if you go into their resources and their developer resources, you will see that they have them for Zigbee, for Matter, and for other technologies as well. In fact, if you go into solutions, you can see they've got Green Power, they've got Jupiter Mesh, Matter, RF4CE, Smart Energy, and of course still Zigbee. All of this stuff still in here. There are videos, there are documents, things like that you can look at to learn about their different specifications. Then you have the LoRa Alliance. You can guess what they're about. They're about LoRa and LoRaWAN, right? Once again, we come here and we can go into the resources and then specification documents, and technical documents and technical recommendations. And then we can read the different specifications for the standards. Then you have Thread. Thread is another IoT wireless protocol system, and it's based on 802.15.4 in most implementations. And you can go into the specification here, and you can say you want to read the fact, you can look at information for developers, and so forth. And then you can go in and actually look at the specification as well by simply providing your contact information, and they'll give you access to the spec. Then you have the International Society for Automation, or of Automation rather, the ISA. When you look at them, they have various publications as well, and some of these are transactions, and this is a collection of publications going back to, I want to say 1981 or 2 time frame, somewhere around there. So quite a number of years they've been involved in industrial automation type systems. And they also have various certification programs. And of course, what do you know? ISA 100 wireless. And so this is a wireless specification for industrial implementation. And then of course, you also have more general, but important. And I really love this organization. And I really encourage you to take a look at them if you've never looked at them before and you work in the IT space. That is INCOSE. INCOSE is the International Council on Systems Engineering. And they just have some excellent publications from their journal. And they also have a systems engineering handbook. The SE handbook is just a great single document giving an overview of the systems engineering process. So everything from requirements engineering all the way through to production. And so they cover the whole spectrum of product and solution development and implementation. Just a really great wealth of information. They also have a YouTube channel. If you're into this kind of thing and you like to listen to talks about systems engineering and so forth, they've got some great discussions on their YouTube channel as well. So definitely a great organization. And their standard, if you will, is the Systems Engineering Handbook, which is based on the systems engineering body of knowledge effectively. Okay. So a really, really good organization. I can't say enough about them. And that is just one brief introduction to standards organizations. There are, as I said, many of them that are out there. And so there are a lot of other organizations that you'll find as you begin working in the industry. Some of them are very niche, and they develop very specific standards for very specific use cases. And some of them try to develop more general standards. But there are many organizations out there. There are standards that you can learn about and understand in order to best understand how these systems work in your environment.